Looks like we are ready to go. So, hey everyone, hope you're doing well. It's been a fun day. I'm sure you've seen all the presentations that are going on, especially with the experts panel. We've been having amazing MCs. Laura and Han are really killing it. And today I wanted to bring something completely different from what we've been talking about on the table. We've had presentations, on AI from a detail. We've had cold outreach workshops. We've had asking the questions, but I kind of wanted to turn a bit more technical and talk a little bit about self-driving cars. So, just to give a bit about an intro about me myself. So I'm actually Shri. I'm 14 years old, so my first year of high school, and I've been in the TKS program for 9 months now. So this is actually my first year in TKS Innovate, and I've built projects such as detecting lane lines, detecting cars. I've been working on detecting skin cancer as well, and I've even went all the way to building a real self-driving into how I built the self-driving car and all the technical aspects to it. I want to take it back to Lex Friedman. And basically, if you don't know who Lex Friedman is, he's actually an MIT researcher, and he has his own podcast known as the Lex Friedman podcast. And I remember there was a podcast interview where he interviewed Sebastian Thrun, who's actually known as the father of self-driving cars. So basically, if you go back to 2004, he led something known as the DARPA Urban Grand Challenge with Stanford, and he basically proved that it was possible to build a self-driving car that could actually drive in desert areas. And Stanford was awarded 2 million. They got a great crash prize for winning it. But putting that all aside, I remember Sebastian was talking on this podcast, and basically he was talking about his drive to get into self-driving and why he thought self-driving was an interesting problem. And he said something that I found to be really interesting, something that's been stuck with me, something that I've really encapsulated to be my mission, or kind of why I'm really into self-driving cars and why I really work on this problem. And it's the fact that 1.35 million people every single year die as a result of driving on the road. And this sounds kind of casual, I'm sure you've heard this statistic thrown around on the road. I'm sure you might have heard it from your friends, but I can doubt whether the fact you really internalize what this means, right? What this statistic really means is that humans, like us humans, we've been making tremendous progress in almost every single field, right? We've talked about gene editing. We've talked about hacking our brain with brain-computer interfaces. We've gone all the way to the moon and Mars. We've been seeing with Perseverance, and we were able to build companies like SpaceX who are having missions to become an interplanetary species. But we haven't solved the fundamental problem of driving. I found that to be insane. People have to risk their lives just to go to work every single day. I just find that to be insane. It says to even drive to my friend's house, I'm putting my life on the line on a road. And we're living in 2021 as well. This stuff shouldn't happen. And I find this really interesting. I've known friends, I've gone through experiences where, I've had friends who've actually been through accidents. And, it's a very traumatic experience, right? You never really realize how significant an accident is until you actually get involved in it. So, for the past 2 months, I really tried to encapsulate this. I really tried to, see if it's possible to solve the problem instead of trying to, complain about it to my parents and trying to say, be a better driver. Why can't we just simply take the human out of the equation? So for the past few months, I've been working on building a self-driving car, and that's exactly what I'm here to talk about today. So, just to talk, reiterate a bit about why self-driving really is the future in the first place. Generally, I like to, bring it down to three main terms. So the first one is the fact that we, theoretically speaking, can reduce global car accidents by 94%. And what this basically means is if you go back to the 1.35 million deaths every single year that occur, and you really look at the root cause, why are these accidents happening every single year, right? You notice that 94% of them are caused by human error. So for every 9 out of 10 car accidents that happen, the cause is a human. It's not a mechanical or hardware error from the car itself. It's the human driver who's always at fault. So theoretically speaking, if we take the human out of this overall equation, we can save more than 1.1 million lives every single year. And I just find it to be extremely insane. And by taking out the human out of this overall equation, you now get this chain reaction where you get increased productivity, with respect to traffic, with respect to accidents and detours, right? You get more productivity and increased flow of traffic because now you're not dealing with traffic and all other issues and whatnot. And, looking at this from an economic perspective and a financial perspective, finance is decreasing as a result of the fact that you're not paying as much for insurance anymore because now you're near guaranteed safety from your point A to point B while not going through some sort of car accident or interference by some other person because now there's no human. And when you really bring this all together, like when you look at it, from a futuristic perspective as well, all of this really will create a sustainable future, especially with respect to, resource depletion. Going through a car accident itself, from a government's perspective, having to repair the road or having to pay insurance itself is a very costly process. So all of this will create a sustainable future, but not only for our people, but also for our resources. So, getting into the nitty gritty details of self-driving, let's talk, a little bit about the self-driving pipeline and how it works. So generally, I like to break the pipeline down into 5 main steps. So the first one I say is like computer vision. So basically in a self-driving car, we generally have, different sensors. For example, we use cameras as one of the sensors in our self-driving pipeline. So how do we extract features? How do we learn from cameras to make, better predictions as the way we drive? Sensor fusion is a bit more different. It's a bit about how do I use sensors like radar and LiDAR and all these spatial sensors that give me an idea about how far cars are and how can I make that into one global 3D space. And then from there, you get something known as localization. And localization basically addresses the question, where am I with respect to like a map? So for example, I look at like Google Maps, right? Where is my car with respect to Google Maps? And as a quick hint, GPS is not enough. And now what happens is when you use all this data, you're not able to, figure out like what path do I want to take? But that's exactly what path planning is. Like, what is the best way for me to drive while ensuring, I go to my selected route. And then control is just, making smaller tweaks, making sure we drive properly and drive on the line. And that's kind of, software like PID controls gets it. So, putting that all aside, let's talk a bit about what sensor fusion really is. So, just as I mentioned before, sensor fusion is all about taking multiple input sensors from LiDARs and radars and whatnot, and using that data to be able to create one global 3D space. So for example, this is an output from a LiDAR sensor. So LiDAR stands for light detection and ranging. And the TLDR uses laser beams it emits laser beam waves to an object and it measures the time it takes to go and come back. And using that, it's now able to figure out how far an object is. And radar is a bit different. Radar uses radio waves as well. So, the concept is pretty straightforward. And basically, generally, we fuse these sensors together. That's the way sensor fusion works. We take these points and now we create one global 3D map. So that might look like this, for example, where we have like LiDAR point clouds. And what happens is generally, what's really interesting is when you look at this problem of sensor fusion, right? We have all this data, but what's really interesting is that where am I with respect to those points? And what this basically means is say that, I had a point that says like, there's an object 2 meters in front of me and I had another point that says 3 meters in front of me, right? How do I know what exact angle, what exact heading I am in that direction from? Because I could be anywhere within that 2 to 3 meter radius where it would make sense as a possible location, but what is the exact location with respect to my previous updates and the exact direction that I'm going? And that's kind of just one of the pipelines of the self-driving process. So for example, here's kind of just a simulation of solving the sensor fusion problem. So here you can notice that if you look at this video, this is just a demo of me running a sensor fusion algorithm in the simulation. So this is known as a Kalman filter. And basically what this does is, you notice here we have these blue points and we have these red points. And what you notice is that these blue points are like radar sensors and the red are like a LiDAR measurement. What happens is you can now get these green triangles. And these green triangles are kind of like our predictions, right? They're telling me where I am with respect to those points. So, as I drive, I use like these past predictions, and that's exactly what I've been talking about over here. We make a prediction as to where we are, and then based on that prediction, we make an update based on that. So that's exactly what Kalman filters are. And from there, we get into computer vision, right? How do computers see, how do cameras see the world, and how do they perceive it around us? So we use something known as a convolutional neural network. Basically, what that means is I kind of scan the image in a sense. I have an image over here, and how do I scan the image and extract features from it? So that's exactly what a convolutional neural network does, or a CNN, right? It breaks down the images and finds a pattern. So, if there's a car, it'll learn to recognize the car. So, you notice here, we have this picture of a house, and what happens is when we pass it through a convolution, we're now able to, extract features that take out all the unnecessary noise, with respect to making the algorithms computationally efficient and making sure that we're able to detect this in real time. We need something that can actually work. So, here's just an example of what I've been talking about right now with respect to CNN. So here's a CNN where I've been working on, detecting cars, and I've been working on detecting lane lines as well. So this is like, the TLDR of what computer vision is. Localizations, I think, to be the most fascinating of all the other tools. So, we just talked about sensor fusion, right? We talked about, getting our data from LiDARs and radars, and now we just talked about computer vision as well, being another source of our input data. Localization is something completely different. So here's just an example. Let's say, I give you this picture of the world map. Where am I? I'm sure nobody has no idea where I am. I could be, I could be in like Brazil or even like the USA or even all the way to like Australia or China. But now let's say I give you the single data point, like a radar or a LiDAR measurement. Now I give you the single data point. Now you know where I am, probably, right? Now you're not only able to pinpoint the exact country I'm in, but now you know the exact city I'm in, Paris, France. And that's exactly what localization is. And just like I mentioned at the beginning of the presentation, GPS is terrible. So it has an accuracy of 3 to 10 meters, which doesn't work. So, we could be driving in a lake and the GPS could tell me to, turn left and then turn right. It's not necessarily giving me an accurate estimation. I could even be hitting a pedestrian. So we solved this problem using something known as a particle filter. And what that basically means is, let's say, I had this car over here as denoted with this green dot. And I have all these red measurements, right? These red dots are kind of like my possible initial starting point. So, for example, that could be like the 3 to 10 meter radius. So I can, use GPS as my initial estimate. And now I have put all these possible red dots as locations where I am within the 3 to 10 meter radius. And what happens is now, as I continue to drive and make progress, you see that our estimation increases, right? We're able to get a lot more of an accurate estimation because the weights of each possible location does not work. So that's exactly what particle filter is. So you notice here as the car drives, it's able to improve its position. And that's exactly what I've been doing over here. So this is just, yet another example of a simulation that I've been working on. And here you notice that this is a car that's running through a localization algorithm. So as the car drives, it has this blue circle that kind of, tags along with it. And this is exactly the estimation of the particle filter. So, for example, here using our sensor fusion data, you notice here with which are these green lines, right? As you take in this data with those black landmarks, you're now able to, compare them to some sort of, higher GPS map that we can use to really help figure out where we are. And now that we've gotten this data, we've got the data from sensor fusion, we got this data from localization, we know exactly where we are, we know the route we want to take. How do we get there? And how do we make sure that we can create a path while we're ensuring, passenger comfort and passenger safety with zero collisions? And that's exactly what pathfinding answers. So we use something known as a finite state machine to get this done. So what that basically means is, given the map, so the overarching like Google Map as an example, given like a Google Map, and given the route that we want to take, so like the route being like from point A to point B, like maybe like go straight and then turn left and then continue to go straight, right? And using predictions. And basically what predictions means is, let's say when I'm driving, I need to make sure that I take a path with respect to time. And that's the most interesting thing, is that even though I might have another car driving beside me on the left lane, and even though I can predict possible trajectories, I need to make sure that the car at maybe like 5 seconds from now won't be in the same path where I am or won't collide with me. So you need to make sure that you need to be able to not hit the car while you're making your path with respect to time. So you could use something known as like a Gaussian naive Bayes algorithm, for example, which is exactly what I did. And now based on that, you get, your behavior planner, you feed this into this FSM, the finite state machine, and using that data, you get a suggested maneuver. And that's exactly what's going on here. So this is just an example of what a finite state machine would look like for the overarching TLDR. So, for example, if I wanted to change lane, then I decide to maybe change left. And then from there, I go back to making sure that I stay on the lane. And what happens is you compare this with something known as polynomial trajectory generation algorithm, which I'll not get into today because it is technical in nature. But here, just as Kabir linked my article in the chat, you can find the technical stuff in there. But here's just an example, what a simulation would look like, right? I've decided that I wanted to turn right because the car ahead of me is driving pretty slow and there's nobody on the right lane. So, using that data from sensor fusion, using that data from localization, I'm now able to create a path. So, I really hope you kind of see how this all ties up, right? This is just, for me personally, it's truly fascinating. I get all this data in the first place, and now every single step of the self-driving process ties in dramatically. And when we get this path, right, we decide that, we want to drive properly, we want to drive straight. Well, if you go back to this simulation, right, you notice that the car isn't necessarily centered on the lane, right? It's more veered towards the left. So how do you make sure it's in the center? And we generally use like a PID controller to do that. And well, what this basically means is that it's a special type of driving control where it uses something known like the derivative and integral and something known like a cross checker, which I won't get into, but using certain values and seeing how far it is from the center of the lane, it's able to use those values to help figure out, well, how can I make sure that I'm staying the center of the lane, especially like if you even notice the car over here, it's leaning towards the lane on the left. So how do you make sure your car's perfectly in the center without, being able to collide with other cars? And, just going back to, a quick recap, I think you kind of seeing where we're going with this now. We got our computer vision at the beginning, we got sensor fusion, right? And now we got all these data sources, and now we use that for localization, right? We figure out, where are we with respect to the map, and where are we with respect to this global system? And using that data, we need to make sure that we plan out the perfect route while making sure that we are with respect to time of the other cars, while making sure we're going on our desired route. And from there, we make minor tweaks with the control throttle of KIT. So this is exactly what the final product looks like. It's a bit underwhelming, but due to COVID and circumstances, I wasn't actually able to run this on a real self-driving car, so like with the hardware and with the lidar and sensors and everything. But there's kind of a simulation to make up for it. And what you notice over here in the simulation that we got the path plan working. And if you notice at like the beginning of the GIF, you notice that the traffic lights red. So we now have this car that can also detect traffic lights as well, right? Using that computer vision data, we can detect traffic lights and other objects. So you notice here it's deaccelerating, and that now when you get that green light, it starts to accelerate. So I think, from my perspective, I think the future is really cool. And, with what's going on with technology such as, AI, BCIs, and even self-driving cars, that's really, starting to develop dramatically. And, I hope we can really create a future where, we can actually have a jet-free collision in the world where we don't have to put our lives on the line when we go to drive to like our friend's house. So that's it from me. Here's kind of my contact information. If you want to know more about me, here's just my email. Here's just my personal website, and I believe my Twitter will be linked in the chat as well, Kabir, if you can get onto that. And yeah, thanks so much for listening. Happy to answer any questions.